Here's an overview of some of the concepts for quiz 4. Remember, we've got these 5 questions, 5 sort of topics on the quiz. Let's start with MO theory here. So I've got some of our key information here. We had this nice diagram. This is sort of the key diagram you need to know for MO theory, along with all the key rules you're going to need to remember, right? Paramagnetic versus diamagnetic. The definition of bond order, half the bonding electrons minus the anti-bonding electrons, and how bond order determines the strength and distance of the bond. So what a larger bond order means is that the bond is stronger. A stronger bond has a larger bond energy, and that stronger bond also pulls the atoms in closer together, making it a shorter bond or a shorter bond length. That key diagram, remember, looks like this with the 2s down here, 2s antibonding. The p orbitals combine in this way here with the pi 2p for most atoms coming lower than the sigma, but that is flipped in this case. So for O2, F2, and Ne2, those do end up flipped. Just a review of how that MO diagram works. Again, in terms of what you need to memorize, the key thing to memorize is this idea about for which ones the pi is lower than the sigma. For the diagram, you can sort of remake that using your basic rules of how MO diagrams work. Again, for each individual atom, let's say I'm doing N2 here, say. Each N has a 2s and 3 2p orbitals. The 2s orbitals combine to make bonding and antibonding. So that gives us sigma 2s and sigma 2s star. That's the same sort of diagram as we had for the 1s and 1s bonding and antibonding orbitals in like hydrogen. For the 2p here, the way those orbitals work is that 2 of those 3 overlaps are pi, so we have this sort of pi overlap above and below the plane. We have this pi overlap going this way. So these 2 are going to be pi 2p orbitals, and then the third one is this orbital, where we do have a sigma 2p orbital. So again, since there's 3 2p orbitals, that's why we get these 3 bonding and antibonding combinations. Remember, anytime we get bonding, we get antibonding. So there's 2 pi 2p orbitals, a sigma 2p orbital, 2 pi star 2p orbitals, and then way up high in energy, a sigma 2p orbital. So again, you don't need to remake this diagram every time from scratch, but again, it's not too hard to remake if you remember the rules. Again, we always get a bonding and antibonding combination from each set of orbitals that mix. And since there's 3 2p orbitals, we have 3 bonding and 3 antibonding orbitals, where it turns out that 2 of them are pi, 1 is sigma. And again, this is the usual ordering that does get flipped for, right, for O2, Ne2, and F2. Okay, now that we have that diagram, let's do the example problem. Okay, so for CO, since that is not one of those 3 exceptions, the MO diagram there will be this diagram. Then we just use our normal rules, right? So we have to fill this with electrons. In our MO diagram, it's the valence electrons. So if we look at carbon, where it is in the periodic table, it has 4 valence electrons. Oxygen has 6. That makes 10 valence electrons we need to put into this diagram. Again, we fill from low to high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, remember, just like for atomic orbitals, we put 1 electron spin up in each of these orbitals first before we pair them up. My arrows here are a little bit messy. I'll rewrite those. Spin up, spin down like that. And that's our MO diagram. We can also now answer these key questions about it. We have, is it paramagnetic or diamagnetic? Well, since all the electrons are paired, it will be diamagnetic. Remember from our key information, again, even going back all the way to exam 1, if it has 1 plus unpaired electrons, it'll be paramagnetic. If there are 2 electrons in each orbital, it'll be diamagnetic. Okay, our next step then is looking at the bond order. So bond order, we need to know that formula. Bond order is 1/2 bonding minus anti-bonding, where we're counting those electrons. In this case, the bonding orbitals, if I sort of highlight them with this red here, I've got the 2s, the 2p. So those 8 total electrons are going to be in bonding orbitals. And then if I look at my anti-bonding orbitals, I just have this 2s star orbital. So 1/2 8 minus 2 gives us a total bond order of 3. Which orbital contributes more to the bonding orbitals and why? This is has to do with sort of electronegativity and the Z effective of each atom. In this case, because we have 2 different elements with different electronegativities, carbon's valence orbitals might have started up here, 2s and 2p. Oxygen, on the other hand, if we thought about its starting valence orbitals, they would start lower in energy, 2s and 2p. That's because oxygen has a greater Z effective, which means that its orbitals are lower in energy. It'll take more energy to pull the electrons away from oxygen. And so as a result, the key rule for MO theory here is that the more electronegative element, or the element with the greater Z effective, contributes more to the bonding orbitals. So O, because greater Z effective. So in this case, if we think about like this 2s bonding orbital here, the electrons, to minimize their energy, will spend a little bit of time near carbon, but they'll actually spend a lot more time near oxygen. So that bonding orbital will be this sort of orbital that looks something like this with C and O, where it's again spending more time near oxygen because of its greater Z effective, greater electronegativity, which causes these starting orbitals to be lower in energy. The rule is that each orbital will look most like the orbitals that are closest to energy. So this bonding orbital will look more like oxygen. This anti-bonding orbital will look more like carbon. Okay, for the ions, the only difference here is how many electrons we fill into the diagram. CO+, we only need to fill 9 electrons. CO2-, since we had 2 valence electrons, we fill 12. So the resulting electron configurations will look something like this. So for CO+, we have to remove an electron, so it's just sigma 2p1. That then, when we look at the magnetic properties, since we have an unpaired electron here, it's going to be paramagnetic. The bond order, we removed one of our bonding electrons, so this bonding electrons will only be 7. So 7 minus 2 divided by 2 will give us a bond order of 2.5. For CO2-, we need to add 2 electrons, so that's then going to be this same diagram, but we'll add 2 electrons up here. For CO2-, that will give us an MO diagram and electron configuration that looks like this. If we look at how those electrons are arranged, that pi star 2p, there's 2 orbitals up here, and there's 2 electrons. That's going to be 1 electron spin up in each orbital. I can sort of jot that down below here, what this will look like. Pi star 2p. So since we will have only 1 electron in each orbital, we'll have 2 unpaired electrons, which will also make it paramagnetic. In this case, when we look at the bond order, we'll have 1/2. We still have 8 bonding electrons. But now we have, if we count up our anti-bonding electrons, 2 and 2 more here. So we'll have a total of 4 anti-bonding electrons, which gives us a bond order of 2. Now to determine the bond lengths, we use our key rule here. The larger the bond order, the stronger and shorter the bond, which relates to our bond energy and bond length. So we look at the bond orders of each of these 3 species. CO has the largest bond order. That's going to make it the strongest, shortest bond. So if we look at who's going to have the longest bond length, that's the opposite of the shortest. So this is going to be the smallest bond order, which would be CO2 minus. The largest bond energy, that's going to be our strongest bond. So that's going to be our strongest one, which will be CO, which has the largest bond order. So that's our basic, really everything we can do with molecular orbital theory. Again, all goes back to just knowing this picture and then what the bond order is, paramagnetic, diamagnetic, all of those key ideas. Okay, the next example problem I have is on intermolecular forces. So again, the key thing with intermolecular forces is knowing which molecules have each force. Again, for hydrogen bonding, we need to have an H bonded to NO or F. For dipole-dipole forces, that's probably the hardest one to figure out since that's true for those polar molecules. And to make a polar molecule, we need to have the bonds polar, which means we have a difference in electronegativity between the two elements. And then we need to make sure that those bond dipoles don't cancel out. So a good example is something like H2S. If we look at the electronegativities here, the electronegativities are different. H2S, if we look at its Lewis structure, is tetrahedral in its electrons, and therefore has a bent molecular shape when we just look at the shape of the atoms there. For H2S, sulfur is more electronegative, so there's a bond dipole here, pointed from hydrogen towards sulfur, and because it has this bent shape, those bond dipoles will not cancel. There'll be a net or overall molecular dipole pointed. When we sort of look at these arrows, there'll be a dipole pointed from bottom to top. That's going to then make the molecule polar. So that's sort of why H2S is going to be polar. Remember, a good hint there is that lone pairs on central atom will usually tend to make our molecule polar. Okay, dispersion forces are easy to identify because they're present in all molecules, but remember that we need to think about the size of that force too. And the idea there is that the size of dispersion forces is just directly proportional or related to the size. So if a molecule is twice as big, it will have roughly twice as strong dispersion forces. So as the molecules get quite large, dispersion forces get quite strong. Then again, the way we're going to determine boiling points is by looking at the IMFs. So if we have overall stronger total IMFs, that will be a higher boiling point. To identify the stronger total IMFs, we need to look at all of the different IMFs. So we need to compare how much dispersion IMFs does it have, what dipole-dipole forces does it have, what hydrogen bonding does it have. So we just need to sort of think about adding together the contribution from each of these, where if a molecule doesn't have any hydrogen bonding, say, then that won't contribute at all. But again, we need to look at sort of adding together all the different terms, right? Remember that because dispersion forces increase with size, for large molecules, dispersion forces will just sort of outweigh everything else. If a molecule is much, much bigger, it will have stronger IMFs because of those bigger dispersion forces. Another thing that comes up a lot when we look at different molecules is that hydrocarbons with CNH only are nonpolar, so those only have dispersion forces. For other molecules, we'll just need to use the Lewis structure and be a CPR to determine the polarity, just sort of like our H2S example up here. Okay, with that out of the way, let's look at our example. CH3, CH2, CH3. Again, we could draw out the Lewis structure. It looks something like this. But again, we can also identify that that's a hydrocarbon, just CNH only, so it's only going to have dispersion forces. There's no hydrogen bonding possible, and again, there's no dipoles in hydrocarbons because the bonds are not very polar. Now for CH3, CH230, CH3, again, another hydrocarbon, so only dispersion forces. CH3, CH2, NH2, again, if I sort of think about what the Lewis structure looks like, I'm going to have N bonded to H over here. This NH bond means I have hydrogen bonding. Anytime I have hydrogen bonding, I'm also going to have dipole-dipole forces because remember, the definition here is that hydrogen bonding is a special strong type of dipole-dipole force. So by definition, if I have hydrogen bonding, I also have dipole-dipole forces. So that gives us all three present in this molecule. CH3OCH3, on the other hand, here if I look at its Lewis structure, just drawing sticks for the hydrogens for now since I don't want to write them all out. Here's the Lewis structure. I have this oxygen atom here. I have no CH, I have no NH or OH type of bond in this molecule, so I don't have hydrogen bonding. But if I look at this central oxygen atom, it has lone pairs. The molecular shape around that oxygen will be that sort of tetrahedral with 109-degree bond angles, and I will have polar bonds because, again, of oxygen being more electronegative at 3.5 versus 2.5 for carbon. So this molecule has polar bonds with this bond dipole pointed toward oxygen, and because it's not in a perfect sort of linear symmetric shape, these bond dipoles won't cancel, and I do have an overall polar molecule. That's generally going to be the case if I have one of these electronegative elements in a organic molecule like this. That will generally make it polar. So in this case, I have dispersion and dipole-dipole forces. Okay, to arrange the substances by boiling point, we need to now determine which substances have the strongest intermolecular forces when we add up the contribution for all of them. So in this case, the first thing I would look at is the size, because size is going to determine the dispersion forces. And again, if one molecule has huge dispersion forces, that'll just outweigh all those other contributions. So in this case, if I look at the sizes of these, A and B are pretty similar in size, as is D. So A, B, D, similar in size, which means that they're going to have similar dispersion forces. But if in contrast, C here, again, it's very hard to write out because there's 30 CH2 groups in the middle, but again, if I just keep writing out lots of squiggles there, it's this much, much larger molecule. And so C is just going to have the strongest IMFs because it has very strong dispersion forces. So that will put C at the highest boiling point over here. Now for A, B, and D, since we have similar dispersion forces, when we think about for A, B, and D, the total IMFs is going to be dispersion plus dipole-dipole plus hydrogen bonding. So for A, B, and D, they all have pretty similar dispersion forces, so that factor is going to basically cancel out. In that case now, since the dispersion forces are roughly equal, it's these extra dipole-dipole and hydrogen bonding forces that are going to make the difference. So now, when I compare those, A has just dispersion forces. It doesn't have any of these extra forces, so that's going to make A have the lowest boiling point. Now, if I look at the next ones here, between B and C, between B and D, D has dispersion and dipole forces. So that explains why D is going to have a higher boiling point than A because it has extra dipole-dipole forces. But B will have the same dispersion forces, very similar dipole-dipole forces as D, because they both have dipole-dipole forces. But it's also going to have these extra hydrogen bonding forces. So that's going to put B at the highest boiling point of those three, and D somewhere in the middle here. So A, D, B, C is going to be our ordering. Again, thinking about the logic here, these dipole-dipole forces are going to be similar for D and B are going to be sort of similar in that regard, and so what puts B over the top compared to D is these extra hydrogen bonding forces. So again, we've got to compare all different factors. Again, C, when we compare it, since its dispersion forces are so much bigger than the other ones, that is just going to outweigh the extra contributions of these two terms up here because it's such a large molecule. Okay, our next example problem is on phase diagrams. So for phase diagrams, you need to know the different phase changes. We have 6 different phase changes that you need to know. Solid to liquid, liquid to gas, gas to solid, and back and forth. So you need to know those words so that you can identify where each phase change occurs, or label a phase change if you're just given solid to liquid or something like that. The triple point comes here at this point where 3 phases coexist at once. The critical point up here is where we lose the distinction between the solid, liquid, and gas phase. So above this point, there's no longer a equilibrium between liquid and gas. And above this point, if we go up here, we're not going to any longer see a vaporization or condensation phase change. The liquid will just sort of slowly get more and more gas-like as we go out to higher temperatures. Again, the lines show the equilibria and phase changes. So again, on this diagram, if I look at, maybe I'll label this in green. This green line here is the solid gas equilibria. So the green line is where these two phase changes occur. Then if I keep going here, I have this line right here. This is the liquid gas equilibria line. That's where these phase changes occur, vaporization and condensation. And in the same way, if I look at this line right up here, solid to liquid, that's where melting and fusion can possibly occur. Okay, let's do the example problem then. This 1 atmosphere line is on here for because this gives us, right, this is going to be basically normal boiling point, and this right here is going to be the normal melting point, right, because 1 atmosphere of pressure is the normal pressure, so that's what you're going to see if we do an experiment just out in the room as opposed to in some sort of pressure vessel or under vacuum or something like that. Okay, so if we look at our questions about this phase diagram, if the temperature is raised at a pressure of 1 atmosphere, the substance boils at 185. So we can go through and label, right? We always have solid over here. We always have liquid over here, gas over here. For A from 50 to 400, that's this line, 50 to 400. I can see 185 is important, but that is not the boiling point. This is a solid to liquid phase transition, which is melting. So that one is going to be false. The liquid phase of this substance cannot exist under conditions of 2 atmospheres at any temperature. Well, we go to 2 atmospheres up here. We can just sort of go over. I would say right here we do have a liquid state right up here. So again, I would say false. We would have a liquid at, about 285. Anywhere at about 285 Kelvin plus, we'll have a liquid state. If we did the same thing at, say, 0.5 atmospheres, then we would no longer be able to have a liquid state. The triple point occurs at 165 Kelvin, so this is the triple point down here. I would say yes, that's about 165 Kelvin, so that's true. At a pressure of 1.5 atmospheres, the melting point is approximately 370. Let's go to 1.5 atmospheres, that's right here on the diagram. We'll look for the melting point. The melting point is the solid to liquid phase transition. This is about 230 Kelvin. So that's going to be false. 370 looks like more the boiling point again. So false. About 230. Critical point occurs at approximately 1.7 atmospheres and 410. This is the critical point up here. That's at 410 and about 1.7 atmospheres. So that looks good. Yes, that does match our graph. The liquid phase is denser than the solid phase. To get the density, remember that we have to look at what happens when we increase pressure. So the rule here is that increasing pressure, increasing pressure favors the denser phase. So in this case, when we increase pressure here, we go from liquid to solid. So that's going to mean the solid phase is denser, so false for F. Okay, when we went back and through this, it turns out the correct statements here are just C and E. Draw a heating curve, temperature versus heat added, showing what would happen as T increases from 0 to 500 Kelvin at 0.5 atmospheres. So that's this line right here at 0.5 atmospheres. We're below the triple point pressure. So for G here, what's going to happen is we can see we're going to heat it up. We'll heat the solid at this point right here, let's say about 120 Kelvin, say. We have a solid to gas phase transition. That would be called sublimation. And then after that point, we have a gas. We're just going to heat the gas up more. The way a heating curve works here, remember, is that we see a flat line at a phase change, because at that point the extra heat that we add is just going to go into doing the phase change rather than increasing the temperature. So if I plot temp in Kelvin here and heat added, we're going to start down at 0. We'll have a certain amount of heat that's going to cause us to increase our temperature at 120 Kelvin here. We'll do a phase change, and then we'll start heating the gas, which will cause us to increase our temperature further. So right here, this is our sublimation solid to gas phase change. Here we have the solid, here we have solid and gas in equilibrium, and here we have just the gas only on our heating diagram. So generally, adding heat increases the temperature, but during a phase change, the temperature remains constant as the added heat goes to convert from solid to gas in this case. Let me make that just a little bit less blurry there. Okay. Now, our last sort of big problem on the quiz is method of initial rates. For method of initial rates, the experiment is that we measure the initial rate, dependent variable, for experiments with different reactant concentrations, which are independent variables. To solve that, we first write the rate law for the reaction. So this KAB, right, this is assuming that the reaction is like, something like 2A plus 3B goes to products. A and B here are our reactants, right? So whatever the reactants are, those go in these terms in the equation right here. Then we're going to do our comparisons to find the orders. So we look for trials where only one reactant concentration changes. When we do that comparison, we can use that to determine how that concentration affects the rate. We can get an equation that looks like this by dividing those two sort of rate laws. Remember that the meaning of each order is sort of how that reactant affects the rate. So for 0th order, that's the case where the rate is independent of concentration. So if I say doubled the concentration, I would see 1x or unchanged rate. In that equation, what that means is that 2 to the 0 is equal to 1. So the concentration factor here, if I double the concentration, that goes here. The order, if it's 0th order, is up here, right? So 0th order, that's the 0 up here in this equation. Then the 1 is, right, that the rate is unchanged, goes up here. So unchanged rate. So in this case, the rate is unchanged, and that's shown right here, that 2 to the 0 is equal to 1. First order is very simple. That's linear relationship, so doubling the concentration will cause the rate to double. Tripling the concentration will cause the rate to triple. Very familiar direct or linear relationship. Second order is this very strong relationship where the rate depends on concentration squared. So in that case, say tripling the concentration would cause the rate to increase by a factor of 3 squared, which is 9. So that's that very strong relationship in the case of, because I've got my colors backwards here, but tripling concentration, that's this 3x there. Okay, then in the last step, we'll solve for the rate constant k. Okay, so here's an example. We have the following data. First, let's do step 1. So step 1 is to write the rate law. So that's going to be rate is equal to some rate constant k times, in this case, my reactants are ClO2, to some unknown power x, so the order in ClO2, times OH minus to some unknown power y. Again, remember x and y are called the orders. These are the concentrations, and then k is the rate constant. So the goal of this procedure is to determine the orders x and y and the rate constant k. Now, we're going to do our comparisons. So I want to look for trials where only one reactant concentration changes. So 1 and 2 is a natural thing to try to compare, but in this case, ClO2 changes and OH minus changes, so I can't use that comparison. But if I look at 1 and 3, if I go from 1 to 3, ClO2 goes from 0.05 to 0.1, so that doubles. OH minus, we can see 0.1 to 0.1 is unchanged, or no difference there. So that means that the effect we saw on the rate is going to be all related to the ClO2 concentration change. For what happened to the rate, we went from 5.75 times 10 to the minus 2 to 2.3 times 10 to the negative 1. If you can't see exactly what that factor is, just do the division. So we're going to compare 3 to 1. That means in math here, again, if you can see that this is what this factor is, that's fine, but otherwise we can just do the division. The division here is 2.3 times 10 to the minus 1 over 5.75 times 10 to the minus 2. So again, this is sort of rate 3 over rate 1 is equal to ClO2 3 over ClO2 1. 2, in this case, the order here we called x. So this rate 3 over rate 1, if I do that division, this turns out to be 4. So that's by what factor the rate changed here. This factor here we know is 2. We just could see that by inspection. 0.1 over 0.05 is 2. So 4 is equal to 2 to the x. What value of x makes that work? Well, x has to be equal to 2. Again, we just have those 3 common orders. You can guess and check 2. So 2 squared is equal to 4. That works out. And so it's second order in ClO2. Our next comparison then needs to determine OH minus. So we've got x solved. Now we need to get y. So if we look at to get y, we need OH minus to change, but ClO2 to be constant. So a good comparison there might be 4 to 3. In this case, we have an unchanged ClO2 concentration. We have OH minus doubling. And we have, if we look at what happened to the rate, 1.15 to 2.3, the rate doubled as well. So when we compare 4 to, I guess I want to compare 3 to 4. Because I like to make comparisons where things double, or it's opposed to going down. So when I do that comparison, I see that the rate factor here, by the factor by which the rate increased, was 2x. So the rate factor here, so the rate increased by a factor of 2. That's going to be equal to the concentration factor here, which is 2. 2, in this case, the order is y, since this is OH minus that's changing. So 2 is equal to 2 to the y. And in that case, again, we don't even really need the math as much here. I mean, we can see that in this case, y has to be equal to 1. And you could also just sort of see this by inspection. In this case, when we double OH minus, we double the rate. That's a direct or linear relationship, which is our mark of first order, right? So first order, doubling concentration causes the rate to double. That's a linear relationship, which is a first order relationship. Okay, at that point, now we have the orders. Now we can do step 3. We're going to plug in and solve for k because that's our last unknown. So in this case, we have rate is equal to k, ClO2, our x is 2, so ClO2 squared times OH minus to the first power. Anything to the first power is just itself, so that sort of drops out here. And now to solve for the rate, we just have to divide both sides by all of these concentration, or sorry, to solve for k, we have to divide both sides by all this other stuff, ClO2 squared times OH minus. That will get k by itself, so that cancels, that cancels. And now we can get this final result and plug in. I'll just plug in trial 1, rate 1 over ClO2, 1 squared times OH minus from trial 1. That's going to be equal to k, which is, again, if I start plugging in, 5.75 times 10 to the minus 2 molar per second over ClO2. In this case, for trial 1, that was 0.05. So 0.05 molar squared times OH minus was 0.1. When you go through and do that in your calculator, you should get our final answer. When I do that, I get k equals 230. 1 over molar squared second squared. Again, to get the units here, we just need to look at what cancels. So molar cancels, and this molar is inside of the square, so that gets squared. So when we look at everything that comes through there and doesn't get canceled, we have a 1/seconds from there, and we have a molar squared on the bottom from here. Again, this molar canceled with that molar, so that gave us our final unit on the rate constant K. In terms of what that looks like on your calculator, just to show that, something like this will work. Again, we need a parentheses here to force both 0.05 and 0.1 to be in the denominator there. Okay, so that's method initial rates. Again, the order in each reactant. I guess we can write down the final rate law here. This is our value of K, 231/molar squared, and our final rate law here, if we write that down, is rate. It's this thing we wrote down, but then we sort of moved it around. Rate is equal to K ClO2 squared times OH minus. So that's our final rate law here for method initial rates. The problem here we have is the types of solids. Here's the sort of review sheet. Again, you can look at this from the slides here. A lot of this is sort of review of previous chemistry. Metallic bonding, as the name implies, occurs in metals. Ionic bonding occurs in ionic compounds that are made up of positive cations and negative anions. Remember that you do sort of need to know your polyatomic ions here. So the cation is typically a metal or NH4+. The anion is typically a nonmetal or some sort of polyatomic ion that we have from our list that you sort of need to know for class and lab. Molecular is just anything with a Lewis structure, and covalent network, you sort of need some help to know that it's covalent network. That has to be some sort of extended crystal structure. Again, some examples: graphite, quartz, diamond, things like that. Covalent network, again, always going to be nonmetals because it's a covalent compound. Okay, so we can categorize each compound by the type of solid that it forms. NH4Cl here. If we look at that, this is, again, you just sort of have to know that prior information. This is NH4 plus cation. You have to identify that ammonium cation, and then it has a Cl minus anion. So this has a positive cation and a negative anion. That makes it an ionic compound made up of those two ions. NH3 is a normal substance that we sort of draw a Lewis structure of. There's the Lewis structure. If we draw a Lewis structure of it, it's a molecular type of solid. Diamond, again, that's an extended structure with carbon making 4 bonds in all directions. That makes it covalent network. Graphite, again, a different sort of structure. That's those sheets of carbons in sort of extended ring type structures. So we've got sheets of carbon atoms, but same idea. They're bonded in all directions in these sheets, which makes it a covalent network solid. We can't draw individual Lewis structures of individual molecules in these substances. Copper, if we look at where it is on the periodic table, it's a metal. So that makes it an example of metallic bonding. So that's sort of everything for this first half of the content for exam 2. And all the content that is on that quiz for Wednesday.